So in today's class, we are starting with the second part of thermodynamics. We already covered a lot of things yesterday. Today, let's start with specific heat capacity and what is latent heat. So let's understand first what is specific heat capacity. So for example, if you have a bowl and you're heating this thing and you have to raise the temperature of it, yes? So if in simple language, if I speak what is specific heat capacity, it means it is the amount of heat required to raise the temperature of 1 gram of substance by 1 degree Celsius. So this is what specific heat capacity says that. So 1 kilogram, I mean, not 1 gram, but yeah. So specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram of substance. This is known as specific heat capacity. And we denote specific heat capacity with the letter smallest. So the smallest letter will be specific heat capacity. Moving forward, we will be also discussing about the latent heat, which is represented by ML. I will be telling you what is it. Usually we have latent heat of fusion, latent heat of vaporization, and latent heat of vaporization, fusion, and the freezing one, I think, yeah. So let's start with the first important topic, that is specific heat capacity. As I told you, it is represented by C also, and it is also represented by S, so it's the same thing. So for example, if you see Q is equals to MC delta T, then C is your specific heat capacity. But also if you see Q is equals to MS delta T, then it is also the same. So I already told you the definition, and the formula is this one: Q is equals to MC delta T. So it's better if you want to use C, use C. It's not a big problem. If you want to use S also, it's the same. Well, so specific heat capacity is usually different for every other substance. So you will be asking, they will be asking you the questions like, what is the specific heat capacity of iron, or what is the specific heat capacity of water, or what is the specific heat capacity of ether, or whatever substance they will be giving you. They will be giving you the mass, they will be giving you the temperature, heat, and they will ask you simply. So as you know, this SI unit of heat is joule, so you don't have to worry about this thing. But let's find out the what is the SI unit of, or what is the derived unit of specific heat capacity. So you know the formula is Q is equals to MC delta T, so which can be written as Q upon MT is equals to C. You know Q is joule, so instead of Q I will be writing joule. Instead of mass I can write kg. Instead of temperature I can write Celsius, yes, or Kelvin, whatever I prefer. So here this thing will be in joule per kg degree Celsius. The mass is clear, the temperature is clear, or the temperature either can be in Celsius or Kelvin. Yesterday I gave you the relation how you can calculate. It's simply 273 plus degrees Celsius. Okay, so now you know the difference, what the definition of specific heat capacity. Let's do a simple question and then we can move forward. So in the question they have asked you how much energy, means how much heat, is needed to raise 2 kg of water from 20 degrees Celsius to 50 degrees Celsius. So what is given? Let's understand what is given first. Let me check whether the recording is happening. Yes. Okay, so given is the mass, that is 2 kg. The temperature they have given, initial temperature is given as 20 degrees Celsius. The final temperature they have given as 50 degrees Celsius, and they have asked us what is the heat, and it's for water. And for water, C is usually 100 if I'm not wrong, in calories. And if you talk about in joule this thing, then it is 4180, but in calories it is 100 calorie. And yesterday I told you guys, if I remember, that 1 calorie is equals to 4.18 joule. So if 100 calorie will be how much? 418 joule, yes. So 1 calorie, maybe specific heat capacity is 1000, then yes, it should be 1000 in this thing. But anyways, we can use this thing. Okay, so they have given us mass in kg and this in Celsius. So since this thing is given in kg Celsius, we are going to use 4180. And if they would have told us to use 1000 calories, then we use a different thing. But now we will be using a specific heat capacity as 4180, joule kg degree Celsius. Okay, so this thing they will give you in question, so you don't have to remember. Anyways, let's come back. So the formula is Q is equals to mc delta T. Q is what you have to find. M is what they have given. M, the mass is 2 kg. 2 into what is C? 4180. What is delta T? Delta T means T final minus T initial. The Q is equals to 2 into 4180 into T final minus T initial means 50 minus 20. If you want to convert it in Kelvin, then also the answer remains same. So when you find the difference, the answer is always same. Doesn't matter. You can put in Celsius because we are considering this. Put it in Celsius. 4180 into 2. 4180 into 2 will be 8360 into 30. This will be around 2,50,800. Okay, so Q will be 250,800 joule. So it will be around Q 250.8 kilojoule if they ask in kilojoule. Okay, so this kind of questions are quite easy. So you just have to implement the formula, and the formula is Q is equals to mc delta T. So they will give you everything. They will be giving you the mass. They will be giving you the specific capacity. You don't have to remember, guys, this 4180. They will give you in the question. They will write in the bracket like this. The C is 4180, or the C is 1000, or the C is whatever according to the material or according to the substance. Okay, so I hope this thing is clear to most of you. Now we will move to latent heat. Latent heat is another important concept, and usually it is defined as the latent heat of fusion and latent heat of vaporization. So let me use this thing with this thing. So latent is the amount of heat energy required to change the substance. For example, if I want to change something from solid to liquid, so I will be implementing some heat, yeah, some energy. So the heat energy I will be requiring to change the substance, uh, the how to say, the state from solid to liquid. So I have to input some energy in it. So this energy will be my latent heat of energy, and latent heat of energy is represented by ml. So L is always given. L is latent heat of energy, M is mass, and Q is heat. So now you know two formula which we have learned so far. The first formula is specific heat capacity, that is QMC delta T or QMS delta T, but use C, it's better. And the other one is Q is equals to ML. So now you know the specific heat capacity, now you know the latent heat. Okay, latent heat is can be fusion. Fusion means when it is converting in from solid to liquid, and when it is getting converted from liquid to gas, there will be vaporization. So this thing will be known as the latent heat of vaporization. So these are the two important latent heat. I told the third one in the beginning of the lecture, which was something which I'm not sure yet. But for now, we don't have to focus. We just have to focus on this two. All right. So I hope the latent heat is clear to all of you, and what is the specific heat, that is also clear for both of for all of you. All right. So let's do a question, and then we can move forward with the other concept. Please, Thomas, do this question and tell me the answer. Thomas, are you here or?
Yes, sir. I'm solving the question.
Oh, okay, makes sense. So the question is, how much energy is required to completely boil 0.5 kg of water at 100 degrees Celsius?
The answer 1.13 into 10 is to 6 joules.
1.13 into 10 raised to 6 joules. Okay, so they have asked you the energy, which means Q, and they gave you the mass as 0.5, and they gave you the temperature, that is 100 degrees Celsius, which means that the boiling point of the temperature is 100 degrees Celsius and the freezing point is 0 degrees Celsius. So you don't have to do anything with it. It just simply says that the water is getting boiled. And the latent heat constant, or L, is given as latent heat of vaporization, is given as 2.26 into 10 raised to power 6 joule per kg. So they have asked, the formula Q is equals to m into L. So simply put the formula, that is 0.5 into 2.26 into 10 raised to power 6, which will be equal to 1.13 into 10 raised to power 6 kg joule. No, it's just simply joule. It's because this joule will get cancelled out with this thing. Anyways, the kg will get cancelled out with that kg. So this is the answer, and in general, the SI unit of Q is joule. So I hope this question is clear, and now you must be able to do the questions regarding or related specific heat capacity and also latent heat of vaporization or fusion. So I got a graph for you, and this graph is very important. Maybe they can ask you in question in exam. I'm not sure, but this is important. You have to remember that, for example, if this is solid, if I am putting heat, then it will get converted into liquid. It's gonna be stay liquid till this thing will be known as latent heat. This thing will be known as latent heat. So all the straight line, the flat regions, they are known as the latent heat. So this is fusion, QF, ML, and this thing will be it will be your slope region. So in this, your temperature is getting increased. Again, there will be a flat region, and that this will be your latent heat of vaporization. So vaporization, and again it's gonna boil. So the flat regions are your state change occurs, means state is changing here. The temperature, this thing is the state is changing from solid to liquid. Here also flat region, so it is latent heat, and this is your temperature increase. Okay, and this is temperature versus heat graph. Okay, now we are coming to a very important concept known as enthalpy. So enthalpy is technically nothing but simply your heat. So but they just gave you a fancy name for this, but the definition is the same. And yesterday we studied the important concept of internal energy and the work done, and the if you remember the formula, delta U is equals to Q minus W. This was the formula which we have studied yesterday. So change in internal energy is your total heat minus the work done. So this was the first law of thermodynamics mathematically. So that's what we are studying here too. So in enthalpy is written by denoted by the letter H. And if they are talking about delta H, they are talking about the change in enthalpy. So in physics, enthalpy is measured as a total energy in thermodynamic system. It includes your internal energy, and they also includes your work done. So delta H is equals to delta U plus P delta V. This will be your enthalpy. It's technically the same. If you look carefully what we have studied yesterday of first law of thermodynamics, we have studied something U is equals to Q minus W, yes? And what I said to you, that enthalpy is just a fancy term for heat. So if you rewrite this thing, it is what? Q is equals to U plus W. And what is W? Yesterday I told you that work done has two formula. One is P delta V and the other one is NRT. So instead of W, I can write here Q is equals to U plus P delta V. And in just replacing Q with H, it is U plus PV, which is the formula for enthalpy. So it's just the first law of thermodynamics technically. Just they gave us the letter with H, and that is enthalpy. So enthalpy is nothing but a measure of total energy in thermodynamic system, and it includes your internal energy. It includes your microscopic and it can microscopic kinetic potential particles. For example, they will be giving you substances, and they will be asking you to calculate what is the internal energy for this particular situation. Then we know what is PV, and we yesterday we did a lot of questions on PV. We calculated the work done from the PV graph also by the area. So if you remember, yesterday we did some questions like this. There were PV graph, and the area of this graph was simply your heat or work done. Sorry. So so this is the formula, and I hope this formula is clear to all of you. And if you have any questions until now, please ask me. Then we are moving forward with the types of enthalpy changes. Okay, the question time. Any questions, please ask.
Sir, I don't get the graph, the above graph.
The PV graph, you mean? I mean, okay. So
Yes, ma'am.
in PV graph, simply you have to calculate the area. So if they will give you a rectangle, triangle, circle, or whatever, you just have to calculate the area, and whatever the area will be, it will be your work done. And yesterday we did a lot of questions on it. Okay, I think there are no questions except this one, so we can move forward with the types of enthalpy.
Sir, the latent heat graph.
Okay, the latent heat graph. So latent heat graph means when there is a change in state, for example, from solid to liquid, the graph will remain the same, because if you know the point, for example, if I talk about heat of vaporization, latent heat of vaporization. So at 100 degrees Celsius, the particles will be liquid as well as vapor. So it's the point, it's the how to say, the threshold point where the change will happen. So that is the reason the latent heat will be straight line graph until there is a change. So at 199.9 degrees Celsius, it will remain liquid, or still 99.99999, it will remain liquid, but just 0.1% shift will change that thing in the vapor. So that is the reason it remains in this straight line. Or for example, from 80 degrees Celsius to 100 degrees Celsius, it will still remain water. So it's a straight line, and when there is a temperature difference, it is going to be like a change in temperature. So like this graphs, like in the way I told you here. All right, thank you. Okay, so no questions, perfect. All right, let's go ahead and we discuss about the enthalpy, types of enthalpy changes. So this is very important, and I think in chemistry also you will be encountering this kind of situations where they will be asking you what is exothermic reactions and what are endothermic reactions. So exothermic reactions are something in which heat is released. For example, if you talk about the neutralization, if you add an acid to a base, for example, if you are doing a reaction of, I'm just doing a little bit chemistry here, but we don't have to do chemistry, but just for your understanding, when you are reacting an acid with a base, then you know that theory of neutralization states that when an acid reacts with a base, it gives you water particles as well as the salt. So when this thing is happening, there is a lot of energy releasing. So when you will see, if you have done this kind of experiments in your schools maybe, so you must have noticed that this beaker turns a little bit hot, or maybe get warm. Why it gets warm? Because there is a release of heat. So this kind of reactions where the heat is getting evolved by some frequency, then this kind of reactions are known as exothermic reactions. So the heat is released to the surrounding, and in this temperature of the surrounding increases, of course, because heat is releasing, so there will be a change in the surrounding, and delta H is negative for this condition. So yeah, this is very important, and the main motive to study this is to understand what will be the value of delta H. So in the questions, if they gave you delta H as minus 360 or something like that, you have to note, simply say that the reaction is exothermic reaction. Okay, and the best examples are combustion. Combustion means whenever you are reacting a chemical maybe, or burning something. Simply when you are reacting something and burning with in the presence of oxygen, then it is known as combustion. And combustion and neutralization are one of the best example of exothermic reaction. Moving forward with the endothermic reaction, the delta H value is positive, so it can be plus 360, for example, or maybe plus 2, plus 7, or plus 8. So in endothermic reaction, the heat is absorbed from the surrounding and temperature of the surrounding increases. So since for example, let's take an example of ice. So you know there is ice particles. So in order to get this ice into water, or maybe melting of ice, I need a lot of heat. And since I need a lot of heat, I will be absorbing all those heat from the atmosphere, and after that I will be absorbing all heat for sure. And since I'm absorbing heat from the surrounding, so the temperature of the surrounding will decrease and this thing will get melt. So the best example of endothermic reaction is the melting of ice. So I can write here melting of ice as well. Melting of ice is an example of endothermic reaction. Photosynthesis is the example of endothermic reaction. If you remember the equation of photosynthesis, if I'm not wrong, let me write it, because it's been a long time that I have studied this. But it is 6 CO2 plus 12 H2O gives you 6 molecules of, one second, C6H12O6 plus 6H2O. Is it balanced? 6, 6, 12, 24. 12. Yeah, I think it's balanced. Yes. So this reaction of photosynthesis is also the example of endothermic reaction, because you are taking a lot of things from surrounding. That is the reason the surrounding temperature will decrease. Thermal decomposition is the example of endothermic reaction too. Okay, so I hope the endothermic and exothermic reaction are clear, but the things which you have to take away, the key takeaway from what I have taught, is delta H. If it is greater than 0, it is endothermic reaction, and if delta H is less than 0, then it is an exothermic reaction. Perfect. And so until now we have studied, I will write here, maybe it's better, and the formula which we have studied till now from yesterday I'm talking. So the very first formula we studied is the first law of thermodynamics mathematically, which is delta U is equals to Q minus W. The second we have studied is work is equals to P delta V. Third we have studied work is equals to delta nRT. Fourth we have studied is the enthalpy one, delta H is equals to delta U plus P delta V. We have studied some formula also for, and just we didn't study it yesterday, but just remember this thing also, pressure is equals to force upon area, because we will be using this also at some point maybe. And what else we studied? What are the formulas are there? Yeah, where is it? Yeah, we studied Q is equals to ML. That's all. Any other formula which I'm missing until now we have discussed? No. Yes.
U is equal to MC delta T.
U is equals to mg delta T. Okay. Yeah, I got you. Q is equals to mc delta T. Okay. Yeah, specific heat capacity. Of course, it is important. That's all. Yeah. Okay. Thank you. So for this thing, the standard conditions for enthalpy is the temperature is 25 degrees Celsius, the pressure is 1 atm, and the concentration is this. So there is a question for you guys. Solve it, and then we can move forward. Question is on your screen. All right, please solve the question. Just give me the answer. The question is: a gas expand at constant pressure of 1 atm from 2 liter to 5 liter, absorbing 600 of joule. Find the change in internal energy.
It's 296 joule.
296 joule. Okay.
296.
All right. Okay. So let's solve it. 296. So a gas expands at constant pressure of pressure is given as 1 atm, and the change in volume is delta V is 5.0 liter minus 2.0 liter, which will be equal to 3.0 liter. Okay, delta V is this. So I can calculate the work done, that is 1 into 3.0, which will be 3 liter atm. But I have to convert.
I can't see screen.
You cannot see screen. Anyone of you cannot see screen, or just none of you?
You can see the screen, sir.
It's visible, sir.
Okay, but now it is maybe visible. I'm sorry.
Now it's visible, sir.
Yeah,
Thank you.
okay. So 1 liter ATM is equal to how much, Hardeep? Huh? Hardeep, you're sleeping?
No, sir.
Then where are you? Okay, so we have calculated the work done, that is this thing. So now you know the formula of internal energy. Yes, delta U is equals to Q minus W, and we have to calculate delta U. You know the heat is absorbing, which means it will be positive. Okay, and minus 303.9, which will be equal to 600 minus 303.9, 296.1 joule. Anyone is having any doubt in this? Laiba?
Yes, sir.
Clear?
Yeah.
Perfect. Amina?
Yes, sir.
Is it clear?
Yes, sir.
Perfect. Thank you. All right, Jawad, please solve this question and give me the answer. All right, rest all of you, please solve the question quickly, and Jawad, give me the answer. So the question is, in an isobaric process, 300 joule of heat is added to a system, causing it to expand. What is the change in enthalpy? And if other people have the answer, please write in the chat box. Hardeep, not Hardeep, sorry. Sanjay, if in this condition, if it is an isochoric process, then also give me the answer. So, Jawad, you give me the answer for isobaric, and Sanjay, you give me the answer for isochoric.
Sir, can you repeat what you said, sir? I didn't hear it, sir.
I'm saying that for the question which is given on the screen, it is written in an isobaric process. So, let's assume that this is an isochoric process and calculate the change in enthalpy.
Okay, sir.
All right, Jawad, no answer, yeah? Okay, 300.
Amir sir, can you hear me?
Yeah, I can.
I think there was a malfunction in my headphones.
Oh, okay.
Headphones. I already gave the answer. I mean, a while ago.
Okay, I didn't hear
I
it.
thought I thought you just
No,
listened that.
no,
I
I
didn't
did.
knew about it.
No,
I'm
actually, I
really
didn't.
sorry about that.
No. So, what is your answer? I didn't hear it. What is your answer?
It's 300.
300
It's
joule.
300. It would be same.
Okay.
Enthalpy will be same as enthalpy.
Yeah. So the it comes here very important concept that in isochoric process, or I mean, sorry, in isobaric process. In isobaric process, the change in enthalpy, very important. The change in enthalpy is equal to the heat added. So the change in enthalpy is equal to the heat added. So delta H will be equal to, since you know the general formula is delta H is equals to delta U plus P delta V. Yes. So in this isobaric process, only delta H will be equal to your change in this thing. So your answer will be same as 300 joule is heat added. And for isochoric process, which I gave the question to Thomas about isochoric process. In isochoric process, you know that there is a change in volume is zero, which means constant. Yes. So if the change in volume is constant, and you know the formula delta H is equals to delta U plus P delta V, this thing will become zero as well. So delta H will be equal to delta U. So in both the condition, the answer will be 300 joule. All right, let's do the other question together, and then we move forward with the entropy. So the question is a 0.5 kg block of metal with specific heat C. Specific heat is, okay, mass is given as 0.5 kg, and specific heat capacity is given as 900 joule kg degree Celsius, is heated from temperature. Delta T is given as, we did this question already, I think, but anyways, let's do it again. Delta H, what is the delta H? Change in enthalpy. Yeah. So the specific heat capacity is Q is equals to mc delta T. Mass is 0.5, 900 into 1020. That will be 450 into 20, which will be 900 joule. And you know this thing, Q is your enthalpy, so delta H is equals to 900 joule. Okay.
900 into 30.
Oh, 900 into 30.
Yes, sir.
Which
Initial
Yes,
temperature
there
is
will be about
20.
13,000 something joules.
1 second, 450 into 20 into 30 from where? Okay, you
50
mean here?
minus.
Okay, 13.
It
So
should
It's
be
50 minus
1350 joule.
yes, not yes, exactly, it is not 20, it is 30. This is 30 because 50 minus 20 is not, is 30 degrees Celsius, sorry. What is the answer? 1350, yes. Okay, very good. Delta
Yes,
H,
sir.
so 1350 joule. Yeah, small mistake. But yeah, make sure you don't do the
Excuse
mistake
me.
in IMAT.
Hello.
Yeah, go for it.
Sir, I have a question. If there would be anything like temperature or specific heat in Kelvin, then we would have to convert the second also now.
You have to convert the second also.
Yeah, like if temperature is in Kelvin, then would we have to convert specific
Okay.
heat in Kelvin to or not?
Well, if you're talking about this thing, if it is in Celsius, if you convert it in Kelvin, then also the delta T will be same. It will be constant. Because let's say 50 minus 20 will be 30. But if you talk about in Kelvin, it is what? 2, 3, 23. And this will be what? 2.
So my question is, if we get in question that temperature is in Kelvin, right? If like we are getting it now in degrees Celsius, but the specific heat is in degrees Celsius, like in unit joule per kilogram degree Celsius. So we will have to convert the second in Kelvin too.
Yeah. Yeah, for sure. You have to convert it regardless. You have to make sure that the units are standard. But for temperature, the difference is same for regardless. So your answer will not change. Perfect. Thank you. All right. So now we will start with the slot, that is second law of thermodynamics. Yesterday we discussed the first law of thermodynamics. So for me, what I have understood from my understanding, second law of thermodynamics is usually up talking about your entropy. Well, the definition is something different, but yeah, from my understanding, it usually talks about the entropy. And it means that the degree of disorderness of the universe is continuously increasing. For example, uh, what is entropy in general, first of all? So let's say you have a lot of particles in this body, yeah, a lot of particles, and now you're heating this thing with certain temperature or certain heat. Yeah, you're giving certain heat at it. So for sure there will be disorderness in these particles. They will collide with each other, they will excite, and they will just disorder with their own self. For example, if there is a building and in the building there are 100 people, and all on the sudden the building has an earthquake. So in that situation, the people will run here and there. So the running of the people will decide the disorderness. So simply entropy means your degree of disorderness. Entropy means degree of disorderness. So the more disorderness it is, the more entropy is. Okay, so this is how. So second law of thermodynamics states that for an entropy for the universe is continuously increasing. So yeah, this is what I have understood from my understanding. But according to definition, well, we have a lot of definitions for second law of thermodynamics, but one of the definition is heat cannot spontaneously flow from a colder body to a hotter body without external world. So for example, if there are two bodies, A and body B, and this is having minus 20 degrees Celsius and this is having plus 30 degrees Celsius, so the heat cannot flow from the colder body to hotter body. So this is what the second law of thermodynamics means. It introduces the concept of irreversibility. So this natural process, there is no irreversibility here. So heat cannot spontaneously flow unless and until, okay, if I can do that, but I have to apply some work here. So this is what second law of thermodynamics means. And in terms of entropy, I already told you the degree of disorderness and the entropy for the universe is continuously increasing. Entropy is a measure of disorder or randomness in a system. It also represents the number of possible microscopic configuration to a system's macroscopic state. So in simple words, this is what I mean. I hope this is clear. So wherever they ask you entropy, simply remember this word, degree of disorderness. All right. And entropy is represented by delta S, capital S, okay? Not small s, capital S. So yes, and the formula which is coming up is one more important formula. Delta S is equals to delta H upon T. This is the formula for entropy, or delta S is equals to Q upon T. because you know Q and what H are the same thing, but different things, different meaning actually, but they both are the same. So delta S is equal to delta H upon T, and delta H is equal to Q upon T. So make sure that you know the formula for entropy, and you also know what entropy means. So the second law in terms of entropy, if I speak, the total entropy of an isolated system can never decrease over time. So if we talk about isolated system, and the best example is universe, it either increases or remain constant in irreversible processes, and delta S for universe is always positive. It is more than greater than zero. Okay, so this is entropy, and we will be doing some questions on entropy, but just key takeaway from what I taught: degree of randomness. This is the main thing. This is the main thing I will say. Yes, or disorderness. Okay, so I will give you two examples of this thing. Let's say I have an example and I'm burning ether in a bowl, and answer, I would like to hear the answer from Zohit if he is here today with us. Zohit, I'm having two conditions. The first condition is I'm having a bowl with ice, and the second condition, I'm having a bowl with ether which is boiling. Which one is having more entropy? Zohit, you're sleeping? All right, let's take attendance, guys. Noor Fatima, you can also put your hand up.
Yes.
Yeah, perfect. Jawad, yeah. Uh, Hardeep,
Yes, sir.
Thomas,
Yes, sir.
Vishal.
Sir, hello.
Yeah, Zohit, where are you?
Yeah, sir. My internet got disconnected.
No, your internet
Something was
doesn't
up
got
with it.
disconnected. Hardeep called you on your WhatsApp and said that, sir, call your name. Come immediately. This is what
Where,
happened,
sir?
yes?
No, sir. I was in class.
No, you weren't.
Yeah, sir. I was taking class. Okay, then if you don't believe me, I did take some pictures.
Now, okay, tell me, what was the
Of
question I asked you?
yeah, sir. I don't remember. Your voice got cut. So
All right, so my question, I have two
can you
containers, and
ask
in
it
one
again?
container I'm having an ice, and in second container I'm having boiling ether. So which one has more entropy?
So ether, I guess.
I guess. Why you guess? Why you're not
Yeah.
sure?
Um. mm, So I don't.
Okay, makes
I don't
sense.
know, sir.
So let's
Yes, sir.
understand this thing. So in the first situation is I'm having ice. Ice is means that it is fixed. It has a definite shape. Yeah. So the disorderness is fixed, and there is no motion in it. But when I'm boiling ether, of course, the particles are colliding with each other, getting excited. They are getting evaporated. A lot of disorderness in that. Yeah. So that is the reason we are having ether as more entropy than ice. So simply remember, entropy means the degree of disorderness, because in past year they have asked two questions from entropy, and the questions we will be solving now. And today's lesson will be a little bit lengthy. I don't know, 10 minutes extra or 15 minutes extra, but just cooperate with me. Yeah. Thank you. So I hope this is clear. Okay, I was on Vishal. Please give your attendance. Okay, you are here. Mariam. I have disabled the mic of Mariam because 1 second, I'm sorry, because there was a lot of, yeah. Amber, here.
Yes, sir.
Perfect. Laiba, here. Perfect. Angela,
Yes, sir.
Mehnur, Talal Ehsan, Amina, Tejas, Zohit is here. Ikra, we have a new enrollment. Ikra, would you like to introduce yourself a little bit? If you can turn on your camera, I'm mic, I mean, not the camera. If possible, not necessarily, but you can write in the chat box also.
Hi everyone, my name is Ikra.
Lovely. That was a beautiful introduction, to be honest. Okay. Anyways, guys, let's come back to the topic, and we talk about Gibbs energy now. Okay, but I hope that things are a little bit clear. Okay, here you go. Okay, Gibbs energy, it is represented by the letter G for sure. Gibbs energy is a thermodynamic quantity in which we will be talking about enthalpy and entropy together. So if I talk about the general formula for entropy, the Gibbs energy, it will be the total Gibbs energy, or the change in Gibbs energy will be your total enthalpy minus. Sorry, I need to turn off the. Okay. So it will be delta G is equals to delta H minus T delta S. Okay. So this will be your formula. And for example, if the Gibbs energy is zero, again, Gibbs energy is zero when the situation is equilibrium. So we can say that delta H is equals to T delta S. And you can find the temperature by the formula delta H upon delta S. So this is the other formula. So if they give you an exam the enthalpy, and they give you an exam the entropy, okay, if they give you both the things, so simply divide both of the things and you will get the temperature. That's the trick. Okay, and the situation should be equilibrium Gibbs energy. So Gibbs energy is a relation of enthalpy and entropy in simple language. If we say Gibbs energy is a thermodynamic quantity that combines enthalpy and entropy to determine whether the process is spontaneous or non-spontaneous. Okay, let's understand what is the meaning of spontaneous. Spontaneous means a thing which is happening automatically without having an external influence on it. I mean that, for example, if something is blowing up automatically, that thing is spontaneously, but something needs pressure, something needs work on done that, so that thing is non-spontaneous. So in English we say spontaneously I spoke that without any reason. I mean, like I just get that thing in my mind and I just spontaneously, I didn't meant it intentionally, but I just spoke spontaneously. But in physics, spontaneous is similar like what I say in English, but something happening without any influence of anything else. Okay, so spontaneous is clear. So whether Gibbs energy will be giving you a perfect understanding whether the reaction is spontaneous, whether the reaction is in equilibrium, or whether the reaction is non-spontaneous. So this is what I mean. So a spontaneous process that occurs naturally without needing external work. I have also written it here. And if the Gibbs energy is negative, the process will be non-spontaneous. Okay. And you know the formula, delta G is equal to delta H minus T delta S. Delta G is Gibbs energy. Yalla. And delta H is enthalpy, T is temperature, and S is entropy. Just delta means change. Okay, and the situation is if delta G is negative, okay, very important. Okay guys, delta G if negative, the reaction will be spontaneous. Make sure about this, you know it. If delta G is positive, the reaction will be non-spontaneous. And if delta G will be 0, it will be in equilibrium. And in this situation I told you, oh, you can even find the temperature. And rather it doesn't matter if they will ask you temperature and they will give you the 3 quantities, and you can find the temperature in that condition also. Okay, so we will do the questions now. Finally, I ask some of someone to give me all the, because we finished this chapter, give me all the formulas which we have studied so far of thermodynamics, and if you have some additional formulas which I think is useful for me, I will take it. So anyone who is going to volunteer me? Because we finished the chapter, we are going to solve some questions now. No one is
Sir,
interested. Yeah, who is that? Vishal?
Sanjay, sir.
Sanjay, yeah, go for it, Sanjay. Okay, let's start. The
Yes, sir,
formula
the first
sheet.
one is
Formula sheet, okay? Perfect. Start.
first one is the ideal gas equation, which is PV is equal to nRT.
Mm-hmm.
The second one is work is equal to P delta V.
Mm-hmm.
And third one is work is equal to delta N RT.
Mm-hmm. And delta N G I will write here because in gaseous state. Okay, anyways. Fourth.
And then we have conversions. 1 atom liter is equal to 101.3 joules.
Okay.
1 calorie is equal to 4.184 joules.
4.184 joule. Okay.
And Kelvin is equal to Celsius plus 273.
Okay.
Then we have the first law of the thermodynamics, which is conservation of energy. Delta U is equal to Q minus W work.
Okay.
And then we have specific heat. So it's Q is equal to MC delta T.
Mm-hmm.
And then latent heat is Q is equal to ML.
Okay.
And then we have enthalpy. Enthalpy is delta H is equal to delta U plus P delta V.
Very good.
And then we have second law, which is delta S is equal to Q by T.
Okay.
And Gibbs free energy is delta G is equal to delta H minus T delta S.
Mm-hmm. Okay. And last condition, if Gibbs energy is zero. Okay.
Equilibrium.
What delta T is equals to?
Delta H by delta S.
Okay. Any other formula which is you think is important, which we should take in consideration?
Exothermic is heat release, so delta H is
Okay.
lesser than 0. And then endothermic, delta H is greater than 0.
Delta H is greater than 0, yeah, for exothermic, or less than?
So yes, sir.
Okay.
Endothermic greater than 0. And then we have so do you want the isothermal, isobaric, that order?
Yeah, if you can give, yeah, for sure, go for it.
So isothermal is temperature constant, delta U is equal to 0.
Isothermal delta U or delta T?
Delta T is constant.
Okay.
Yeah, okay. And delta U is also 0. Adiabatic V is constant.
Okay, you mean isochoric delta V is 0, yes?
Yes, sir. Yes, sir. Delta V is 0.
And adiabatic
Isobaric.
Q is equals to 0. You can see the screen, guys, yeah? Yeah.
Yes, sir.
Perfect. 19. Okay, go for it as the formula.
Isobaric pressure is constant. Delta P is 0.
Okay, what else? That's all? Yeah. And last, area of PV graph gives work.
Okay.
Yeah, revision. I think everything is clear, yeah? And you can just quickly revise after looking this. Thank you so much, Sanjay. All right, so guys, let's do some questions and we are done for today. We have 4 questions to practice from past year. Let's do the very first question from IMAT 2011. So the question is, which of the following system has an overall closest to 0? So they have asked the entropy closest to 0. Means that when the entropy is 0, when there is very, very, very less degree of disorderness or very less movements. Okay, so closest to 0. So let's start from the last. Option E. A metal object is being rapidly electroplated. A lot of energy is coming in, so there is no chance that the entropy will be 0. So the option get cancelled for sure. An object in free fall when it has reached terminal velocity. In free fall, when an object reaches terminal velocity, so it's gonna have velocity for sure. It will come back again, so there will be change in velocity, so the entropy will be, the body is moving, so the degree of disorder is still there, so the answer is not 0. Okay, the third is evaporation of ether. Of course, no, no chance, because a lot of evaporation means a lot of degree of disorderness. So no, zero. A satellite in an orbit of 25,000 above Earth. Okay, this makes sense a little bit, but again, we need to remember that it is in a universe, which means that um, the heat is getting, a lot of heat is getting involved in it while the satellite is getting moved because of the sun rays and everything, and the satellite is in constant motion. So it's still a doubtful for this. Three is getting cancelled. The last one is a weight moving up and down on a spring. So they have asked either closest to zero or very zero. So either one or B is correct, because this only situation says that the object is having a little bit relatively as compared to this three, because this are having a lot of disorderness. But if you talk about the randomness about A and B, we have relatively less as compared to C, D, and E. But which one between A and B suits the best? What do you think?
Sir, beta.
Beta or alpha?
Alpha.
Reason? Do you have any specific reason for this?
Not specific, but I think the um, type of what can I say? I don't know what should I say, but uh, the system, I think, Earth and the satellite, it is way more bigger than the spring.
Yeah,
So there
very
will be
good.
a lot of disorder.
And also the heat is involved. Yes, because of the sun. So that is the reason the answer
Yes.
for this will be A. A is correct. So better excluding, eliminating the options and getting the answers correct. Okay, thank you, Jawad. That's nice answer for sure. Okay, let's move to the other question. 24. 2012 IMAT. A block of iron at 100 degrees Celsius, temperature is 100 degrees Celsius, is transferred to a plastic cup containing of water 20 degrees Celsius. Okay, so now one thing which is important to note, that if they give you two things, two objects, and they have asked you to calculate, or they have said that there is exchange of heat or something. So you know the formula Q is equals to MC delta T, yes? So just simply relate these two formulas. MC delta T of object A is equals to MC delta T of object 2. So whenever you have gonna change this, so simply Q1 is equals to Q2, okay? So it will be M1 C1 delta T means change initial temperature minus, I will use a different pen. Initial temperature, initial temperature minus T final MC1, and now M2 C2 final temperature minus initial temperature. So this thing, I hope this is quite relatable what we have learned for specific heat capacity, but the situation is quite different, and now I'm covering it, that when there are two objects, so simply relate them both. Q1 is equals to Q2, and you know the formula of Q, yeah? And in the same way, you can also relate MC delta T to ML if necessary. So learn how to relate things. Anyways, okay, let's come back to the question. A block of iron at 100 degrees Celsius is transferred to a plastic cup containing water at 20 degrees Celsius. The temperature is given. Which one of the following is not necessary in order to find the specific heat capacity of iron? So we have to calculate the specific heat capacity of iron. So which one is not necessary? So if you see from here, specific heat capacity of water, is it not necessary, Sanjay? If for example, Sanjay, if I'm not having the specific heat capacity of water, then is it possible for me to calculate the specific heat capacity of iron?
So, I think no.
No, yes.
No, sir.
No, not necessary. Not definitely no. Because I must have specific capacity of water. If I'm not having, it is impossible for me to calculate the C1. Okay, so it is important. So yes, it is there. Mass of the block of iron. Mass is not important.
It is.
It is. So this is also not true. Final temperature. Final temperature is not important.
It is.
Mass of water. Mass of water is not important.
It is.
It is. But the thermal conductivity of iron, we don't have to do anything with thermal conductivity. Conductivity is represented by the letter C. So we don't have to do anything from conductivity if we are talking about specific heat capacity. So option C is Not necessary. Okay. Is it clear? Is it very hard or is it very like moderate? Moderate, yes. Perfect. Okay, 25 question on your screen. Very important question. I will read it, try doing it, give me the answer. If not, the answer is not correct, then I will explain. Okay, let's read together. 2012 again. I'm at 2012. At the melting point, which of the following are correct about paraffin wax? And you know, paraffin wax is the compound made up of hydrocarbon. And hydrocarbon are attached with each other with ionic bond or covalent bond, Laiba? Hydrocarbons are attached with each other with the help of covalent bond or ionic bond.
Covalent bond.
Covalent bond, excellent. Perfect. And you must be knowing that covalent bond are quite relatively stronger. Yeah? Okay. So the question is, at the melting point, which of the following solution are correct about paraffin wax? And I told you what is paraffin wax. It is technically a compound which is made up of hydrocarbons, a lot of hydrocarbons. So are correct. The substance becomes more disordered. The wax takes in heat, but its temperature stays the same. Bonds between the carbon and hydrogen atoms are broken. So read the question carefully. Give me the answer with reasoning. You have 1 minute to answer this question.
Sir, 1 and 3.
1 and 3, okay.
Sir, 1 and 2.
Sir, 1 and 2.
Option eta.
Okay, someone is saying option E and someone is saying option. And they both are.
I would say all of them.
Oh, someone is saying all of them. Okay. So the very first thing is for sure correct, yes? Because if you're heating something, it becomes disorder. Yes or no? So 1 is correct for sure. So B and C is incorrect 100%. Let's cancel them. Eliminate them. 1, 2, 3 is remaining. Let's take the second one. The wax takes in heat, but its temperature stays the same. It is the example of latent heat. So yes, it is right. So the wax takes in heat, but its temperature stays the same. The temperature remains the same, but it is taking heat because the reaction is what? Endothermic. Okay, the temperature remains same because I don't know, I am explaining it right, but what I have understood from my understanding, I'm saying my personal experience. When you boil up water, and if you're putting on gas stove or on induction or something like that, so your temperature always remains constant, yes, but your heat is always changing. That is the reason it's not like that I'm increasing the temperature again and again and again and again, that then only the water is getting heated up. If the temperature is constant, still my tea is gonna get I know it will be ready, I mean, yes. So the temperature stays the same. So 2 is correct. It makes sense too. Third one, bonds between the carbon and hydrogen atoms are broken. Okay, this is quite confusing. And someone said 1, 2 and 3. 1 and 2 is for sure, like this E and A is for sure, but let's understand whether 3 is correct or incorrect. As I told you, for example, if you know that, for example, I am having one hydrocarbon, let's say methane. Let's say I'm not talking about this thing, okay? And I'm taking another compound as methane only. So the bond, the force which is present between these two is the van der Waals force. And the force which is present inside CH4 is covalent. And whenever I am heating up a wax solution, so my bonds, the covalent bonds are quite stronger. They don't get broken. They don't get broke easily. But for sure there is a disorderness, yeah, between the compounds or between the molecules. And the molecules are what? Hydrocarbon molecules. And the force which is there, maybe it is London force, or maybe it is dispersion force, or maybe it is van der Waals force, or whatever, that is getting broken. So not my carbon hydrogen bond. So what is the correct answer?
Sir, it will be eta.
Okay, perfect. So the answer is E. Anyone is having question in this?
But sir, beyond the another point that start from solid to liquid now, till the melting point, it's remains same.
Yeah, I don't know what you said, but yes. I'm sorry. Could you please repeat your question? I didn't got you. Because your voice is quite, I don't know, unclear.
Sir, when we start heating up the wax, it stays remains the until the it reaches the maximum point of the boiling. After that, if we apply heat, then it's turn change the temperature, na?
Yeah, that is also correct. At the melting point, yes, you're right. So they have also one more thing. It is talking about melting point. Yes, you're right, Hardeep. You are talking about all the things in melting point, no doubt. The particular point. Okay. So yeah, but if you raise a lot of temperature, of course, the hydrogen and carbon bond will be raising. But they will of course mention in the question. Okay. Last question for today, and we will end the class. Let's do this question, and I will ask a person to do this question. It's from IMAT 2015, and I asked Noor Fatima, please do this question. Thank you. IMAT 2015, and nothing in rocket science. Very simple question. So the question is, an aluminium block of mass 2.5 kg, mass is given 2.5 kg, is supplied with 9,000 joule, means Q is given as 9,000 joule. This is causes a temperature rise by 4 Kelvin. Temperature rise is given as 4 Kelvin. So 10 change in temperature is given. Which expression gives the specific heat capacity data? So assume that the block is solid throughout, there is no additional change and exchange. So standard condition. Noor Fatima is doing this question. A, B, C, D, E. Alpha, beta, I don't know how to say theta. What?
Then I think delta.
Yes, you're right. It's D. It's very simple, right? Q is equals to MC delta T. Q is given 9,000. M is given 2.5. C is, we have to calculate, T is 4. So 9,000 upon 2.5 into 4 is your C. So the answer is D. So I hope this concept is clear, and if you have any questions, again, you can feel free to write me on WhatsApp, and I will be more than happy to clear all the doubts. And if you have any questions regarding anything, you're more than welcome to ask your questions now.
Excuse me.